The third on our list of 12 recent discoveries is that functional sequences of enzymes are incredibly rare. To explain this topic, I have to provide some basic background. So proteins are chains of amino acids that fold into three-dimensional structures, and there are 20 natural amino acids that make up proteins. The backbone chemistry is the same, but the side chains differ. Each amino acid can be represented by a letter, and so a chain of amino acids would look like this, a long chain of a combination of these 20 different letters. DNA is like a different language. It's a chain made up of a different kind of molecule called nucleotides. And there are 4 nucleotides that make up DNA. So it's a language of 4 letters. And so a chain of nucleotides, or a strand of DNA, would look like this. It's A's and T's and C's and G's in many different orders and combinations. The structure of DNA was solved in 1953 by Watson and Crick. We now know that DNA stores information in its long strand of those 4 letters. And in some cases, the sequence of letters code for proteins, and the precise sequence of the amino acids of the protein are critical for the function of the protein. In 1966, there was a symposium called the Wistar Symposium in Philadelphia. It was called the Mathematical Challenges to the Neo-Darwinian Interpretation of Evolution. And one of the topics that was highlighted is that protein sequence space is too large to be searched. So if there are 20 amino acids and L is the length of the protein, let's say 150 amino acids long, then there are 20 to the 150th power possibilities. So mathematicians knew right away that protein sequence space is too large to be searched. You can think of this in terms of a written language. The phrase protein sequence space is too large to be searched includes 50 characters if you include the spaces. For the first position in the sentence, there are 27 possibilities because there are 26 letters plus a space. The same is true for the second letter or the second position in the sentence. And the third. So there are 27 to the 50th power possible sequences. And how many of those are functional? How many of those possible sequences would communicate a sentence that's meaningful in the English language? So that's the question that was recognized to be very important, critical, because the distribution of the protein chain length for enzymes in E. coli is shown here. The peak is around close to 400 amino acids long. So since there are 20 types of amino acids, chains of amino acids that are 300 units long will have 20 to the 300 possible sequences. Since only a minuscule fraction of that can be searched, the question is what fraction of those sequences fold, or what fraction are functional? To address that topic, there are 3 methods. The The first is to simply make sequences randomly and see how many fold. That's called the forward approach. The second is to start with a folded protein and mutate portions of it and try to determine from that the fraction of sequences that will remain folded. And the third approach is to analyze sequences in the protein data bank. That's an informatics approach. The first approach is too slow. It can't be used for long proteins, say proteins of 150 amino acids or longer, like enzymes. The forward approach was used for proteins of 80 amino acids in length. This paper in 2001 reported that 4 out of 6 trillion random sequences bound ATP. Binding ATP is a very low-level function since ATP is a very sticky molecule in the sense that it has several functionalized chemical groups. It's unclear that folding is even required to bind to ATP. Subsequent work showed that a 12 amino acid peptide is able to bind to ATP. Nevertheless, this work shows that only 4 out of 6 trillion random sequences could accomplish the very low-level function of binding to ATP. The second approach was used by Robert Sauer and his colleague at MIT. They studied the N-terminal domain of the lambda repressor protein, which is a protein of 92 amino acids. Its function is to bind to DNA to repress transcription. By combining targeted random mutagenesis of a small portion of the protein with a functional assay to determine the fraction of sequences that were functional, and then assuming that the same statistics apply for the entire protein, they could estimate the fraction of sequences that would adopt this fold. Their estimate is that 1 in 10 to the 63rd power sequences will adopt this fold. The second approach was used again by another group in 2001, and in this work they focused on an enzyme called charismate mutase. This is an enzyme that has 93 amino acids. It's a very simple fold in the sense that it's composed of 3 helices, and the enzyme is a homodimer, so there are 2 copies of this structure that complex together to form the enzyme. By using the same approach of targeted random mutagenesis over a small fraction of the protein and combined with a functional assay that assayed for the activity of the enzyme, and then extrapolating the statistics over the entire protein, they estimated that the fraction of sequences that adopt this fold are 1 in 10 to the 24th. So that's a much smaller number than for the previous example, but that's because this is an extremely simple fold. This approach was used a third time by Doug Axe, who published his work in 2004. He focused his work on the beta-lactamase large domain protein, which is comprised of 153 amino acids. This larger protein has a more complex fold and is representative of large domain proteins. Using the same basic approach and expanding the analysis to include any domain-sized functional protein fold of 150 amino acids in length, Axe estimated that only 1 in 10 to the 77th sequences would adopt any domain-sized functional protein fold. The third approach is a bioinformatics approach. Here, the researchers estimate the sequence capacity, which is the number of sequences that are consistent with a particular fold, and then it's a simple matter to divide by the total number of possible sequences to get the fraction of sequences consistent with that fold. This approach uses existing data for sequences that are known to be consistent with common folds. They chose 10 proteins with very common single domain fold structures. The proteins that they chose also have extensive mutational data. So using all of that data, they constructed models to estimate the sequence capacity for each of the 10 types of fold. The results of this approach are summarized in this table taken from their publication. L is the number of amino acids making up the protein. SC is the sequence capacity, and SC star is the fraction of all sequences that are consistent with that fold. So for proteins with amino acids ranging from 87 to 94, the values range from 10 to the minus 38 power to 10 to the minus 86 power. For proteins with greater than 100 amino acids, the fraction is much less than 1 in 10 to the 100th power. To put these numbers into perspective, the total number of all organisms to have ever lived on the earth is estimated to be about 10 to the 40th power. Recall that for the enzymes in E. coli, most of those proteins are of length 400 amino acids. So for enzymes, a protein of 150 amino acids is very small actually. But for proteins of that length, there are 20 to the 150 power possibilities. And that's an inconceivably large number. Not even a minuscule fraction of that could be searched in the entire history of life on Earth. All along, the important question has been, what is the fraction of sequences that fold? For proteins of 150 amino acids, the reverse approach gave 1 in 10 to the 77th power, and the estimate from the bioinformatics approach was less than 1 in 10 to the 100th power. To put these numbers into perspective, the total number of protons in the observable universe is estimated to be about 10 to the 80th power. These two approaches are entirely independent, and yet they both arrive at the result that the fraction of sequences that fold is inconceivably small. These two facts together pose a remarkable challenge. Sequence space is far too large to be searched, and yet the fraction of sequences that fold into a large domain protein is inconceivably small. So where do the sequences that are functional come from? This is an interesting statement that comes from an article from 2013 called "Close to a Miracle. Researchers are debating the origins of proteins." And in this statement, there's a quote from a protein researcher named Dan Tofik, who unfortunately passed away recently. But I'll just read this quote. "Overall, what the field of protein evolution needs are some plausible solid hypotheses to explain how random sequences of amino acids turned into the sophisticated entities that we recognize today as proteins. Until that happens, the phenomenon of the rise of proteins will remain as Tawfik says, something like close to a miracle. So to summarize this discovery, protein sequence space is far too large to be searched, and functional sequences of enzymes are incredibly rare. No one knows how they were found or where they came from. The functional sequences of enzymes seem to constitute a very large informational discontinuity. Researchers in this field suggest that perhaps functional proteins could be made from a set of much less than 20 amino acids, and that the enzymes necessary for the first life perhaps were much shorter than those that exist today. But that's not the reality that we observe. And there are reasons why a large diversity of amino acids are necessary. And also, there are reasons why the lengths of proteins must be as they are today for enzymes to support life. To date, that research has not led to anything even close to the set of enzymes needed for life. So it seems to me that this discovery does constitute a very large informational discontinuity.